The other two operations, obviously multiplication and division. There's all sorts of different ways of approaching multiplication of functions. This is just one idea. So I now want to multiply the two functions together. And again, the starting point's the same as what I just did with the addition and subtraction, where I'll just draw the two original graphs. But what we do here, the key things to look at is actually the sign of the product of the two. So whether it's going to be positive or whether it's going to be negative, because the key thing we know is when we multiply positives together, we get positive. Multiply negatives together, we get positive. Multiply different signs together. And that tells us the area that the function can travel in. So things to keep in mind here. Now, discontinuities. Once again, any exclusion in the domain of one of the original functions will become an exclusion in the new function. Because again, you can't substitute into that original function. So if you couldn't get an answer in the original function, how can you multiply it by something? X-intercepts are nice and easy, because obviously if we multiply the two graphs together, we get 0. So any x-intercept will remain an x-intercept. Symmetry, some type of symmetry it'll keep, right? But it might change. The middle one's interesting. Odd times even gives you odd. And the top one, you multiply two odd functions together, you actually get an even function. So basically, if they're the same type of function, when you multiply them together, you get an even function. If they're different types, you'll get an odd function. Okay, here's a totally random curve that I drew. Well, I haven't drawn it yet. I've already factorised it for us and made it as a product to make life easy. Now, we've looked at graphs like this and approached it a different way. Because all we looked at before is we said, oh, where does it start, where does it finish, and x-intercepts, and from there we drew a rough curve. This is just another way of looking at the same thing. So there's the three curves I'm going to multiply. X squared, x plus 1's the line, of course, and the cubic. And so what I'm saying is we're going to break this up into regions and work out whether it's positive or whether it's negative. So all of those x-intercepts, they're not asymptotes that I'm drawing in. That's where the boundaries are, at the x-intercepts. That's where the new region will become. And we'll decide, is it going to be positive, is it going to be negative? Because at those points, they will be the x-intercepts. So the first one, well, I know I've got a positive times a negative times a negative, so I know I'm going to be up here somewhere. Then between the next two, I've got a positive times a negative, so that'll be negative. Positive times negative, that's negative, isn't it? So straight away, that tells me something about this graph. If there's an x-intercept there, but it stays negative, that's got to be a turning point. Now, all right, from our other idea, we knew that anyway, because y equals x squared, and we know it behaves like the power. So we knew we were going to have a double root at that point. But it's just a different way of approaching it and coming up with the same conclusion. Right-hand side, positive times positive, of course, is positive. So we know we're in there. There's my x-intercepts. There's what the actual graph, if you can quite make that one out, it's the dark green one in there. Let's make it a little bit easier to see. It's now become light green now that I've got rid of that purple. And that's the actual one. And of course, when you combine this idea with calculus, you can find the actual value of these turning points and things like that. It looks like that's just a straight line. Trust me, it's not. It's to do with the scale that's there, because that turning point must be something very, very small, the y value. So it looks like that is a straight line. Division, a little bit more interesting. Still the same idea. Okay? You sketch them separately, but there's now a key difference. The x-intercepts no longer remain, because whatever function's on the bottom, the x-intercepts will now become asymptotes, because you can't have 0 on the bottom of the fraction. So let's have a look at x plus 1, x minus 2, on x plus 2, x minus 1. Basically, there are 4 straight lines there. The x-intercepts will still decide our regions, but 2 of them will be vertical asymptotes now. So I've made them red, so I don't confuse them with my boundaries. So the red vertical lines are going to be the asymptotes. Bottom of the fraction can't equal 0. Then the regions, there we go, made those blue. So the red lines and the blue lines, they're going to separate the regions where this is going. So we start off. Negative times negative times negative times negative, positive. Then between the red and the blue, I've got positive times negative times negative times negative, negative, positive, positive, negative, negative, positive, 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 negative, negative, positive, 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 positive. Whee. There we go. So we now know where it's travelling. We have x-intercepts at those blue ones. There we go. So I've got to go through those x-intercepts. I suppose the other key feature I could always find is the y-intercept. That's just got to substitute in x equals 0. It'll find that one. But let's have a look at what we've got. We must have a horizontal asymptote here, because there's no x-intercept for me to go into the other region and go up to infinity. So what could it be doing? I mean, okay, it could be coming from the top and turn and go up. Maybe that's a possibility. Or it's going to be a horizontal asymptote like so. Well, let's look at it in a bit more detail, and we know, actually no, because there's another thing we've done. How would I find the horizontal or oblique asymptote of this function? Or I could use the idea of limits. What's happening out at infinity? Where all I've got to look at is the highest coefficient of x. So it saves me expanding the whole thing out. On the top, the highest one would be x squared. The bottom would be x squared as well. X squared on x squared. There's going to be a horizontal asymptote at 1. All right. So it's not actually going to be that x-axis. So 1 is the y-intercept. So clearly it either cuts it or touches that horizontal asymptote, but that's okay. Remember, you're allowed to cut your horizontal asymptote. So let's find that asymptote we talked about. There it is. That's if you did it with polynomial division. Again, you come up with the answer 1. So draw it in. All right, now let's look at this in a bit more light. So yeah, it looks like we've got some sort of hyperbolic shape up here in the top left. It's got to bend towards these two asymptotes. Over on the right-hand side, no. It looks like I'm going to have an x-intercept. So the hyperbola would start down here in the negatives, cut here, and go that way. Yeah?
How do you know it doesn't cut and go above and then go back down?
Ah, let's go back to that fraction we saw before. Maybe it does. Remember, find out if it cuts it. You solve, when you've done your polynomial division, you're now looking at the top of the fraction. Solve that equals 0. So the only time it will cut or touch will be at x equals 0 for this one. Yep. So we've got that accounted for there, but it won't cut it over here. So that's why I know, yeah, it's got to be that sort of hyperbolic shape. In between, what's going to happen? I've got to bend towards this asymptote. I've got to go through 1. Got to go through this x-intercept. And I'm going to bend towards this asymptote. It looks like I'll come up maybe like a cubic or a tan functional, that sort of shape, that inflecting shape. Let's see. There it is. Get rid of the shaded bit so we can see it a little bit easier. It's the darker blue. So many lines there. Of course, when you're doing that, I mean, those construction lines would be in pencil. It would make it a lot easier to stand out. Sine x on x. This is always a goodie. People get this wrong all the time. Because there was a multiple choice question 2 years ago. It simply said, which graph represents y equals sine x on x? I just thought that was a gift. I thought everyone would know what that looks like, but maybe that's just me. Okay. Let's actually construct it to see why it gets its shape. We're saying sine x divided by x. So there's y equals x. Ooh, there's y equals sine x. We're dividing by x. So at x equals 0, something's happening. The initial thought is it's going to be a vertical asymptote, but it's not. And so if you do look back at some time in that past HSC question, you'll notice a couple of the options had a vertical asymptote at x equals 0. Because people go, oh, a vertical asymptote must be that one. Yeah. But when we were from first principles differentiating sine x. Remember we had to come up with that limit to enable us to do it? The limit of sine x on x as x approaches 0 is right. So we must have a point discontinuity rather than asymptote. It'll go in to the point 1. It'll be a point discontinuity because it can't equal 1, but we'll just have a point discontinuity there. So there it is. Limit as x approaches 0, sine x on x is equal to 1. So there, bang, point discontinuity at that point. Okay. That's what it ends up looking like, because what's going to happen, if you think about it, is just saying y equals x, and I'm going to divide it by this sine x. Now sine x is periodic, but y equals x is not. Y equals x is getting bigger and bigger and bigger and bigger. So you're getting this sine x, which is consistently going between -1 and 1, but you're dividing by bigger and bigger and bigger numbers. So its winding gets smaller and smaller and smaller as we go along. And it now becomes an even function because we're now dividing by x, which is negative. And so you get negative divided by negative. So it flips it over. Or another way of thinking about it is sine x is an odd function. Y equals x is an odd function. Odd times odd is even. Remember, multiplication and division are the same when you're thinking about that. So you must end up with an even function there.